Hi, in this chapter, we will treat this not the point mass, but some mass distribution or some rigid bodies rotational motion. We will use angular parameter instead of linear parameter. How did we describe motion? We learned this in chapter 2. We require linear parameters such as linear position vector or linear displacement vector, and the time derivative of this position vector, which is linear velocity, and time derivative of linear velocity vector, which is linear acceleration. Using those three vectors, position, velocity, acceleration, linear position, linear velocity, linear acceleration, we could describe motion of particles. Now, for the rotational motion, we will use, instead of linear parameter, we will use angular parameter. F equals ma. Here, instead of using linear acceleration a, we will use angular acceleration alpha. So we will use not force, we will use torque. Okay. Later, I will relate this torque to angular acceleration. We will find the relation between torque and acceleration, angular acceleration. It's like F equals ma. Torque will be proportional to alpha, angular. So rotational analog of force is torque. It's similar, linear, like x to alpha, x to theta, v to a to force to torque, analog. And torque is defined as r cross f. F is definitely force, right? Force acting on that rotational body. And what is r? R is vector, right? Definitely vector, starting from axis of rotation. R is a vector starting from axis of rotation to pointing to and the position where force is acting. So torque is relative to the rotational axis because why? Force will be independent of the rotational axis, right? But the R changes with respect to the rotational axis. So even if the force is the same, force vector is the same direction, same magnitude. If this is rotational axis, right? If R vector is defined as displacement from the rotational axis to the force application point, right? Rotational axis to the force application point is the R vector. So even if the force is the same magnitude, same direction, 3, the torque increases as R increases. The farthest away, the torque becomes greatest because R vector here becomes greatest. And also, it depends on the angle. Angle between torque magnitude depends on the angle between this R vector and F vector. You can think that, because sine theta, right, only this normal force, the perpendicular component to R, force component which is perpendicular to this R vector matters here. Or you can say that, R normal, which is R vector will have parallel and perpendicular component to the force. This parallel component does not matter, but this perpendicular to the force component matters. This is just conceptual analysis of this equation. For point masses, single point mass, rotating single point mass. This is rotational axis, and this is rotating with angular acceleration alpha, for example, then F equals ma, but A should be equal to force is, we can say, force is R cross F. So let's say this is 90 degrees. So RF is torque. Like in this way, you can find, we calculated this and we calculated this, but we didn't calculate this. We didn't calculate this. But you can calculate this, all these yourself. Okay, as I told you earlier, see, for the same object, rod, if the rotational axis is not the same, rotational inertia is not the same. A solid disk has 1/2 mr squared. You can derive this by yourself. Okay, hollow spherical shell and solid spherical shell. Solid, you mean filled inside. It's empty inside. It's different. And for the same object, if the axis is not the same, see, this is not the same. 1/2 m a squared plus b squared here, only a squared. you can find all these rotational bodies, rotational inertia by integrating this. From now on, we will learn some trick to find this rotational inertia without integrating of rigid body. Very important, some useful theorems. So as I told you, if we know rotational inertia, ICM is about rotational inertia about an axis through the center of mass. For example, rod, rotating with respect to this center. We found that ICM here is 1/2 ml squared, right? If this length is L. Then parallel axis theorem allows us to calculate the rotational inertia I through any parallel axis. For example, what about through this axis? If it rotates through this axis, what is I? For example, this also solid sphere, 2/5 mr squared was I, right? What about through this axis? It's very, very complicated to, integrate this. If you try to find this by integrating this, it'll be really, really complicated to find rotational inertia about this axis.